Hello, good morning, everyone. Welcome to the class. So, this chapter we already started. So, let us continue. So, that for all the arithmetic and logic instruction, carry flags are change. They change. They may change. I mean, they are adjusted. So if like any flag, it should be reset. If it is already reset, so reset. But if it is set, it will be reset. Something like that. So carry flags are affected. So shortly, we can say carry flags are affected. I mean, flags are affected. Carry flag, parity flag, sign flag. So this 8-bit, you can see carry flag, parity flag. Not this 8-bit. I mean, this is the lower 8-bit, and from the upper 8-bit we have overflow flag also. So including these 5 and overflow 6 flags, they are status flags. They are affected. I mean, yeah, during the arithmetic and logic instruction. But some instructions, they are specifically for specific flag, like CLC, clear carry flag. So it is specific for carry flag only. So carry flag will be clear, that means reset. Whatever it is, it will be reset. If it is set, it will be reset. If it is already reset, so unchanged. So something like that. So these are the things we already discussed. And then we also say that there is a similarity but difference between compare instruction and subtraction instruction. And then we also have seen, like if we have an instruction like compare instruction between how these 6 status flags are changed. I mean, what would be how they are affected. And there is another example. And then we say that some jump instruction, they are called, I mean, only one jump instruction, it is called unconditional. And what is the mnemonics for this one? JMP, jump. So it is unconditional. So and some conditional jump instruction, like there are many. If the condition is met, if the condition is satisfied, then it do the jump, otherwise it go to the next line. So mainly we use so far jump if carry flag is set, JC, JNC, jump equal, jump not equal. These are the things. Not all are, you don't have to memorize this thing all. Only if you think that we use, it will be familiar to you. Okay, and then during the loop instruction, we can format it in a void until. So already we use the loop instruction. So it means that I mean, we set the counter, and at the end of the loop instruction, we decrement the counter, and we say that if count value is 0 or not. If it is not 0, so continue the loop again. Do the loop again. So this is about loop instruction. But we can write the loop instruction other format, like while do format. While do format, it means yeah, it check that loop is done or not. If it is not, so it will continue, and then decrement. Yes, so that means the condition is checked at the beginning, and but here, I mean, yeah, but in previous case, condition is checked at the end while do structure. And also you know that this example is very common example. Like if we have a set of data, we can move from one memory location to another memory location in a simplified format, and we can also write it in a loop format also. I mean, using the loop. This is all. And what is subprogram? Subprogram is this is also discussed. It is apart from the main program, we write it separately. It is, I mean, we may have to use it many times, so it's better to keep it separately. And yeah, and there is some format about how to write a subprogram or procedure. Like we should put the name, then we should write a proc for procedure, and then near or far. and this is we already discussed. Okay, and loop instruction. So loop is basically LWP. Loop is the commonly used instruction. We use it, and already we use it. We have the idea. Now let's see a few more examples. Yeah. So look at here. Given the following sequence of the instructions, explain what happens if they are executed. So if we have this instruction, like let us have a look. Move DL comma 05. That means 05. So nothing means decimal. It's not hexadecimal. Okay. So 5 decimal and hexadecimal set. So that means DL is loaded with 5, and then move AX comma 0A00. So basically, yes, 0A00. So X will then move DS comma X. So that means this two line is for initialize the data segment, right? Initialize the data segment, this two line. Okay. Move AX comma some number and then move DS comma AX. So that means initialize the data segment. Then move SI comma 0. Okay, fine. And we set the counter move CX comma 0FH. 0FH in hexadecimal. What is the decimal number? 15, right? F is 15. So 15. CX is 15. Count value is 15. And now increment SI. SI was 0, now it is 1. And then compare square bracket SI comma DL. So that means compare a memory location, right? A memory location with DL. What was the DL value? 5. So that means memory location value. So what is the memory location? Exact memory location here. If you look at here, so you know the memory location, it is the offset of the memory location. So offset of the memory location, then offset is, we know that I mean always, if it is not, I mean normally, so the data in a data segment, so it means that DS colon offset. Here data segment is data segment has the base, data segment register at the base of the data segment, and offset is defined here. So that means what is DS? DS is 0 A 0 0 and offset is 1. So 1. Yeah, this is the thing. So all are in hexadecimal. So this is also H. This is also H. So it means the what is the physical actual address? Actual address is 0A, or physical address 0A001H. Okay, so that means, you know, so what does it mean? That it actually compare this memory location data with DL. Is it 5 or not? Is it 5 or not? Loop not equal. If it is not equal, if it is not 5, then come again in this loop. Here again it will go to the next memory location. It will go to how many times loop will continue? How many times? 15 times, because counter value is 15. Okay, so is it okay now? Do you understand this one? What is the memory location address? We know that a square bracket with memory location offset is here 1. But what is the base address? Base address is, because always the data from data segment. So data segment base is given here in the first, second two line, second and third line. Okay, so that means this is the memory location. So that means from 0A001 to 15 memory location. It will compare 15 memory location with 5. If it is equal with, if it is not equal with 5, it will check 15 memory location. But if it gets 5 in any memory location within a 15, then it will stop comparing. All right, so that means at first through the loop SI points to the memory address 0A000. At the beginning it is 0A000, because SI beginning 0, it starts 0, then it becomes 1. So the next instruction compares the contents of this memory location So content of this memory location with the contents of DL, is it 5 or not? So actually it is, there is a mistake actually. It's if it should be 0A 001, because before comparing S is becomes 1, SI becomes 1. Actually it should be 1 here also. Yeah. If the data held at 0A001 H is equal to 5, the 0 flag is set, otherwise it is reset. So if it is equal, then compare. If you do the compare, that means subtraction, 0 flag will be set. Your result will be 0. Otherwise it is, and loop not equal instruction then decrements CX, making it, so it was F, CX was F, now it becomes E. Then check for CX equal to 0 or 0 flag is 1 or not. So it check CX equal to 0. If neither of these two conditions is satisfied, program control is returned to the instruction with the label again. So it will come to the again. And this causes the comparison to be repeated for the examination of the contents of the next byte in memory. So on the other hand, if either condition is satisfied, the loop is complete. In this way, we see that the loop is repeated until either a number 5 is found or all the location in the address range from 0A001. Sorry, it should be 1 to 15. So 15 means 1 to F 000F. This is 15. Okay, so it is okay. Here are tested and found not to contain 5. If there is no 5, that means it will continue the loop for 15. So 15 memory location 0A001 to 0A00F. It will continue. Check. If anytime, if any of the memory location has 5, then it will out of the loop. That's it. Is it okay? Do you get it now? So what about the other guys? Is it okay? Okay, all right. So then, yeah, this is about the yeah. So about the use of loop not equal. Loop not equal. If so, the loop. If I mean we use the loop, but loop not equal we didn't use. So here is an example. So that means once the any of the condition, two condition actually, either any memory location is 5. If it is happened, then it is out of the loop and it will come to the next line. Okay, but if it is not, then it will continue for 15. So 15 times actually. So 15 times, then it will out of the loop. Next slide. All right. So now there is another example. It's about the delay loop. Delay loop is, like, to calculate a specific time delay, we need to calculate the number of times the program will loop around itself. We already have the idea what is loop. Okay, how to form a loop. But sometimes we may have we have to make a loop that the purpose of it is to consume time only. I mean to delay time. If you can remember, okay, I can give you an example. Like in the road, you can see on the road, red light is on for 15 seconds or green light is on for 25 seconds. Okay, so that means, or you can see that in some traffic signal there is a counter, step down counter is set, like for 25, say 25, 24, 23 is count. When it becomes 0, then another signal is on. So it's like actually, so when the red light is on, for example, for 15 seconds, so that means once the light is on, 15 seconds should be spent at that time. So we can write a program that actually that actually make a certain things continue for 15 seconds, something like that. So it's called a delay loop, delay subprogram, or something like that, delay. So to do this, we need to know how many clock cycles are required to carry out a particular instruction and the processor clock rate. Okay, let us see. You know that, for example, this is a very basic example of delay. Like this is delay subprogram. So delay with the label, for example, delay, then move cx comma n. So n depends on how many time we want to spend time on this loop. That means, for example, red light is on for 15 seconds. So 15 seconds, the microcontroller, this traffic signal, it's automatic, right? So so behind the timing control, there are some microprocessor or microcontroller there. Okay, so that means when red light is on, then it doesn't allow to do any other thing, any green light on or any other thing, or yellow light on. So it's red light on. So once the red light is on, the digital system, either microprocessor or microcontroller, whatever it is, its job is now to spend 15 seconds without doing any other thing. Just just consume the 15 second or 20 second or 25 second. So it's n depends on that second. How many time actually we want to stop in this loop. So actually this loop is doing nothing. Just we are in the loop to consume the time or to elapse the time. Okay. So look at here, delay subprogram, move cx comma n. N is the number, it depends on our time. Then decrement cx. So cx value is now 1 less. And then if it is not 0, come to again in this line. Not 0, del 1. So del 1 in this line. So decrement, again decrement, again decrement. So it decrement until it becomes 0. Once it counter value is 0, then it will come out. So I said you that in a subprogram, from the subprogram we come out using the return. In the last class we said RET, return. So from here we will return back to the main program. Okay. So in the main program we call delay. We call this delay subprogram, and from this is the also simple way we can write our subprogram also. Even though there is some format. So, but without using that format also, this way also we can write our subprogram, like with a label, delay, and then move cx comma, like for example, this is a delay subprogram. And once it is done, finish, then return, RET return. Okay, now what is the value of n it should be? Okay, and let's do the calculation. Before that, we should have some basic information that how many clock paths. You know that all the digital IC, like microprocessor is a IC. Okay, so it's a 40-pin IC. So every digital IC, you can remember in JK flip-flop, different types of flip-flop, counter, all the things they work on clock paths. If you can remember 200 like. So this kind of IC, to make them synchronize, it must work on clock pulse. So this is like a clock pulse. So its period is this one. One clock pulse, the period of one clock pulse is this one, right? This one is one clock pulse. For example, this one is T. Okay, period of one clock pulse. So for this instruction, decrement CX, how many clock pulse it requires? Just for information, just know it that 2 clock pulse is required. So we need 2 clock pulse to execute this instruction. Microprocessor need 2 clock pulse to execute this instruction. Decrement CX. How many clock pulse it requires for this jump? So as it is a jump, it needs something more operation. Something. It's not easy instruction, because it is a conditional jump. When it check the condition, if it is made, then it will do the jump, something like that. So it needs a more clock pulse. It's for 16 clock pulse. So look at here. So for the second line, we need 2 clock pulse. For the third line, we need 16 clock pulse. Okay, and the loop is n times, because n is the number, loop is n times. The loop happened n times. Okay, so it's actually just it's not the n time actually, because n minus 1 time actually basically. So for simplicity we make it n times. Okay, because we already decrement cx, so n minus 1 is n minus 1 times. Anyway, for making simple, so it's 18. So 18 clock pulse is required for n times. Okay, 18 clock pulse. So now if we need okay, another information we need, that is the microprocessor clock frequency, this t. What is the period of one clock? So we know that most of the in the first chapter, you can remember the 8086 microprocessor, it may be 5 megahertz, it may be 8 megahertz, or it may be 10 megahertz. So basically 8086 microprocessor has 3 different types of clock frequency are there. So for example, it's very common thing is the trainer board that microprocessor trainer board that we use in the lab. The clock frequency there is 5 megahertz. So okay, for example, it is 5 megahertz, not 4.91. Make it 5. Make it easy. 5 megahertz. It is 4.91, so it's 5 actually. So integer value 5. 5 megahertz, 8 megahertz, or 10 megahertz. So if 5 megahertz, what is T then? T equal 1 over 5, right? 1 over 5 mega. 5 mega. So it becomes 0.2 times 10 to the power minus 6. 10 to the power minus 6. Okay. So 0.2 times 10 to the power minus 6 is a period for one clock pulse. Is that clear so far? Is it okay? Okay, so this is for, yeah, okay, fine. So this is for one clock pulse period. So and so then we can say if, for example, if we need 100 millisecond, we need 100 millisecond delay. So 100 millisecond delay. So then what can we write? We write that 0.2 times 10 to the power minus 6. Okay, it is 10 to the power minus 6. In MATLAB we write it this way. Okay, 10 to the power minus 6. Okay, just for understanding. This is for one clock pulse period. And how many times, how many clock is there for this loop? 18, right? So times 18, and the loop will continue. It is for one loop. So for n loop times n equal 100 millisecond, right? 100. So millisecond, we can write it 100 times 10 to the power minus 3, right? So then what will be the n? Use the calculator and let me know. I am also doing 100 times 10 to the power minus 3. So divided by 0.2 times 10 to the power minus 6 minus 6 times 18. So what is it? What, sorry, what is the n? What actually you got it? Hmm? What actually you got? Huh? 27,777. Okay, or you can say 78.777. Okay, 27,778. It's around. Okay, or maybe okay, for simplicity we make it is for 27,777. This is 1,000. Okay, so this is the n. So you can see we do some approximation like n, about the n, and also another thing is, you know, during the last time, when actually it becomes 0, it will not come here, it will go to the I mean it actually, once it is done, it will, the last time it actually come out of this loop actually. So that means it's just approximate calculation today. And other thing is microprocessor, we assume it is a 5 megahertz microprocessor. So if it is a 5 megahertz microprocessor, and if we do think that for this jump instruction it needs 16 clock pulse, and for this decrement CX it needs 2 clock pulse, and so approximate calculation is this one for 100 millisecond. Okay, 27,777. We can remember it. It is for, so it is for 100 millisecond. Is it okay? Do you understand this calculation? This calculation is okay for you? Hmm? Yeah, so yes, okay. So this is for 100 milliseconds. So approximate. We are not very precise about it. Or you can see here, actually, if it is like a 4.991, 4.9152, then it is like 27,300. So it's okay. Anyone we can use 27,300. This is also not. I mean, uh, sorry, 273. Yeah, 27,300, yes, or 27,777, whatever any figure we can use. Okay, so this is for 100, approximately for 100 millisecond. So now for 1 second, like sometimes we need 15 second, we need okay, so that means this is the value of n. So now n, we have to load n on in CX, right? CX, but CX is 16-bit register. So it has a limit, right? Okay. So what is the max? It can support 2 to the power. I mean, it can support how? What is the biggest number it can support? 2 to the power 15, right? This is the biggest number it can support. So 2 to the power 15 is what? If you have a calculator, oh, okay, I have 2 to the power 15. So biggest number it can support 32,768. 32,000. So it's still for 100 millisecond, okay. But if it is like a bigger number, like for example, we need a, it is for 100 millisecond. But if we need a 25 second or 100, I mean, or 50 second, then it will be very big. All right. So it will be very big. So CX will cannot support it. So for it's better for 100 millisecond. Okay, we load it. Then how can we adjust it? Like if we need a if we need a 1 second, for example, if we need a 1 second delay. So 100 millisecond is 1 second is how much bigger than 100 millisecond? 10 times, right? 10 times bigger than 100 millisecond. All right. So okay, and for 100 millisecond now, what conclusion we can achieve here? For 5 megahertz microprocessor, if it is a 5 megahertz, for 100 millisecond, we can set n equal to 27,777, or for this one also, any 27,300. Anyone, so you can use anyone. Okay, so this one of these two, this is for 100 millisecond. Okay, now for 1 second or 10 second, so it will be multiple, right? For 1 second it must be 10 times bigger than this one. For 100 millisecond, sorry, for 1 second 10 times. For 10 second it will be 100 times, 100 millisecond. So then what can we do? How can we adjust this program? So then actually what actually we have to do, we have to do, okay, let me clear it. Okay, then what can we do? We write something like that. So we use another resistor. No, sorry, no, L, comma, N. For example, for yeah, 1 second. Okay, 10. What does it mean? So 1 second, I'm just a comment. 1 second equal 10 times of 100 millisecond. Okay, so that's why this 10, we put it 10. Then delay subprogram. CX 27,777. Given CX on given EL jump not 0 delay. Then okay, look at here. What adjustment we have done here? Because we need for example 1 second. Okay, 1 second delay. 1 second delay. So 1 second delay. So first of all, we use another resistor, for example, move BL, 10. Okay, because 10. Why we put 10? Because 1 second is 10 times, then 100 millisecond. That's why 10. And then move CX, we know that what is should be the n value. What should be the n value for 100 millisecond? We calculate it. If it is 5 megahertz, 27,777. Or if it is like a 4.9152, then it is like a 27,300. Okay, so it depends on actually what clock bus we use. Okay, so anyone we can use it. Okay, so we can calculate it, and or we can use it approximately 27,000. It's simple thing is 27,000. Okay, to 27,000, or okay, this is for n. Then decrement CX. If jump not 0, come here again. So it will jump not 0, it will continue. So decrement CX. Jump not 0 again. decrement Cx, right? So that means until Cx value will be 0, it will continue there. If it is 0, then we say decrement BL. Next line, decrement BL. So 10 will be 9, and then jump not 0. If it is not 0, come here again. Come here again. Again it will take 100 millisecond. Again 100. So 10 times it will do the 100 milliseconds. So 10 times 100 millisecond is 1 second. And then once it is done, then it will come out return, because it is a sub program. Is that okay? Is it clear to you? It's okay, guys. So for long time, like 1 second, 10 second, so on, because you know number will be Cx value will be bigger. So Cx, yeah, it cannot afford it. It cannot. I mean, save it. So this bigger number, because it has a limit 2 to the power 15, because 16-bit register. What is the maximum value? 2 to the power 15. So 0 to that number it can support. So that means we can, so that's why for example for 100 millisecond we put the what is the value of n, then later on out of this 10 milliseconds, so this is for the 10 millisecond, so sorry, 100 millisecond. So out of this 100 we use another loop, we use another resistor and another loop, decrement BL and the jump not. So that means main loop inside another loop, something like that. It's okay? Is it clear, right? All of you are clear? Okay, so now it's about the delay subprogram. So this one actually we have to use it on the lab. Okay, we will use it in the lab also, this idea. So just for information, you can now think about it that approximately for 100 millisecond we can write 27,000, around 27,777 or 27,000, because in the lab machine the clock frequency is not 5 exactly, it's from 4.91. We can use anyone. We can use 27,300, or we can use it. And you know that this is the decimal number. So we can also write the hexadecimal. If you convert it to the hexadecimal, it is this one. So we can, it's our choice. We can write it decimal or hexadecimal, doesn't matter. This is about the loop subprogram. Okay, so now we can discuss something extra, something different. That we say that in the next lab, sorry, next week we have a lab, mid-lab exam. So what will be the, I mean, so the syllabus will be, what will be the syllabus? Syllabus is, you know, according to the manual, experiment number 2 and 3, you should read it thoroughly. I mean, A to Z. University, yes, it is on university, because from next week lab will be on university. This is the instruction we got, that just for 2 weeks, I mean, it is online, then after that it will be on university. So that means lab number, experiment number 2 and 3, you have to study them A to Z, because it is it cover, it includes all about the basics of assembly language. So 2 and 3, okay. Paper, it's actually paper based, not in computer, so paper based. So all the information, because we have just only, we don't, I mean, you have a big number of students, so it's difficult to take it on computer. So it on you have to write. Okay, so 2 and 3. So 2 is actually, it's very big. Experiment number 2 is actually basically, it's like a 2. I mean, it's not a 1 experiment. It's like a 2 experiment. 2 is mainly, then 3. 3 actually it's about like you know, we use some special function for display and for From manual, yes, all the things from manual, all the things what actually you have done in the lab. Manual, yeah, just mainly manual. It's huge actually. I mean, it's enough, more than enough. So yeah, so manual, because lab manual you must read thoroughly lab manual. I do not ask anything or anything out of the manual. Is that okay? So yeah, so lab mid exam will be on next Monday. All right. Yeah, there any type of like not only code actually. So basic thing like same like homework 2 and 3, homework 2 and 3. You know homework 2 and 3 like that. Not only I mean code, basic thing like for example yeah. Yeah, lectures lab. I said lectures and lab all are same, because without lab we do not understand lecture, and without lecture we do not understand lab. So it's I will explain it. So experiment number 2, it's like a homework 2 and 3. Okay, homework 2 and 3 means experiment number 2. Okay, because all the A to Z in homework, I mean all the best information on all the things in based homework 2 and 3 is actually on experiment number 2 manual, lab manual. You can see, you can check it. All the things are there. So mainly, yeah, I will explain it, and when I made the announcement, so I will make it clear. Okay, so it's about the lab mid exam. What will be for the quiz? I think it's the time for another quiz. Another quiz. When actually we make another quiz, quiz number 3. When can we make another quiz? 5 to 6. Base depends on average. Next week. Next week Sunday is okay. Next week Sunday is okay. After next week, it will be late actually, because then we cannot take enough quiz, because quiz actually it help you to prepare for the major 2. Okay, so then actually, because we already I mean finish after the major, we already finished 2 chapter. I mean this including this one, it will be 2. Next week Thursday we don't have any class, so Thursday is sorry, I do not get. Thursday we don't have any class, so you want out of the class time next week at this time. Again after next week when we finish all measure. So you will finish all measure this week, right? This week all of you may finish the measure or no? Oh, okay. So you have also next week also you have measure. Okay, yeah, okay. Then okay, finish the measure first and then take the quiz. Okay, no problem. No problem. Okay, so week after, not the next week, week after. Okay, no problem. So all right, but actually then I'm worried that you may have it. So could we manage time? Because we want to take 2 more quiz before the major 2, so that it helps you to be prepared. Anyway, so finish the measure 1 first, then we'll think about the measure 2. Okay, until now, what is the thing that we will have a lab, mid-lab exam next week. So next week, and I will make it announcement on the Blackboard, and yeah, how actually we'll prepare. So it yeah, I will give you the guidelines. And then all right, so this idea, so we what are the things we have learned so far here. We can see that this is a loop, but this loop is for delay, just consuming time. Consuming, I mean, it's just waste time for doing nothing. This is like that, because sometimes we need it. As I give you the example, like red light is on, so it must be like how it will be in the mid-lab. Mid-lab is written base, it's a small course. Yeah, yeah, it is written. So it maybe is one or two code, one or two program you may have to write, and rest of the thing is about basic. Okay, not too many programs, something like a very basic idea. For example, yeah, copy AL data to BL. So move BL comma AL. It's this similar, like quite similar like homework 2 and 3. Okay, so and then for example, we use some directives like X. This is also you got in measure 1, right? XDB 20. What is, yeah, XDB 20? Is it, what is the difference between XDB 20 and XEQ 20? Okay, so what is the difference between two? They are, in some sense they are similar. Like we initialize the X variable with 20, but what is the difference? One is saved in the memory, one is not, doesn't, one is not saved in the memory. So X eq 20, so X equal 20, it is not saved in the memory, but X yeah, DB 20, it's saved in the memory also. Okay, so basic information, DB, then actually something you already got it in measure 1. So just I want that, just read the manuals, and I think homework 2 and 3 also help you. No, I said that homework 2, I mean lab number, experiment number 2. Experiment number 2 in the manual, it actually covers the homework 2 and 3. That's why I said if you study the homework 2 and 3, it kind of it almost 80% it covers, 80 to 90% it covers the experiment number 2. This is, I think, it covers. Yeah. So this is the, I want to mean that I do not want to make it more longer. I mean long syllabus. I just say that if homework 2 and 3 you study, it actually covers the 80 to 90% of experiment number 2. Because experiment 2 in the manual, it has, because it is the basic information of assembly language. Many things are there. So homework 2 and 3, it actually all different types of topics are there, in different types of problems are in homework 2 and 3. This is, I mean. So okay, so my purpose is not to give you, I mean, more job, or I want to include the homework. I do not want to include the homework in the lab exam. I say that if you study the homework 2 and 3, it help you to cover the 80 to 90% of experiment number 2. This is, I mean. Okay. You got my point? Is that clear? Okay, main thing is experiment number 2 and 3. This is the main thing. Now it's actually you think how actually you will prepare. This is your job. Okay, so I mean this is the main thing, that homework 2 and yeah, experiment number 2 and 3. This is the main syllabus for yeah. Okay, so do you have any question for today's class? Or so in Measure 1 exam result is uploaded. Okay, okay, thank you. Okay, okay. So Measure 1 with solution also. Now you have used solution, you have the actual solution. Now you can compare that you where actually you have the mistakes. So hopefully you will get. I mean, you will get your answer that why you get 30, why you get 35, why you get less, why you get more, all the questions in, even if it's still yeah, this is like that. So solution is uploaded on the Blackboard also, you can check your answer with the solution. That's it. And yeah, so hopefully inshallah see you in the next week. And yeah, you have any other question? Okay, okay, thank you all, thank you all. Okay, see you in the next week.